A pendulum of mass m swings on a light string of length L. If the swing hanging directly down is set as the 0 point of gravitational potential energy, I should say if the pendulum hanging directly down is the 0 point of gravitational potential energy, find the gravitational potential energy of the pendulum as a function of theta and L. This is going to require a little bit more thinking here, I believe. Well, let's think about what's going on here. At the highest point here, it has gravitational potential energy. As it swings down, it all becomes kinetic energy. We're trying to find the gravitational potential energy of the pendulum in terms of theta and L. Well, we know that change in gravitational potential energy is going to be mgh. The trick then is going to be finding out what this h is as it moves from its lowest point to its highest point. And to do that, we're going to have to analyze this with a little bit of geometry and trig. The first thing I do here is I take a look and notice that if this is L, then this length also must be L. If I draw a straight line over to the center of the ball on my pendulum, though, this length now is no longer L. It's gotten a little bit shorter. So h is the difference between L and this red line. If we could find the length of that red line, which is the adjacent side of this right triangle, we'd be golden. So let's see if we can't do that. Theta's there. We know the cosine. We want to know the adjacent side. We know the hypotenuse. Cosine of theta, so katoa, ka. Cosine of theta is the adjacent side divided by the hypotenuse, L. Therefore, the adjacent side must be equal to L cosine theta. So this is L cos theta. What we really want to know is this distance here, that h. H then must be the total length of our pendulum L minus this L cosine theta. Or I could factor out the L's and say that that's L times 1 minus the cosine of theta. Now when I go to put that back into my formula here for gravitational potential energy, UG equals mg. Instead of h here, I'm going to put L times 1 minus the cosine of theta. So there's the gravitational potential energy of our pendulum when it's over here at this point. Its weight times the length of the pendulum times 1 minus the cosine of theta, which is really just giving you the height difference from its lowest point to its highest point. Hopefully that gets you a good start on energy. We'll talk more about that in our next presentation on conservation of energy. Thanks so much for your time and make it a great day.